And now we are moving on to final presenter today. And that will be Ken Sweeney. He'll be talking about the evolution of the GBeam and its role for the future of transportation infrastructure. Ken leads the senior management team at AIT. He ensures day-to-day operations are successful and strategic goals are met. I didn't know that, Ken. That's good to know. But he also spreads a lot of information about the benefits of composites to the structural engineering community. He's a real champion for this. He's out there at conventions, seminars, trade shows. He's fighting for composites to become more prominent. And as former chief engineer of the Maine Department of Transportation, he also brings a very deep understanding of the challenges that our DOTs face to this as well. So Ken.
So he neglected to mention that I'm a graduate of the University of Massachusetts and Lowell. It used to be called Lowell Tech, but that was a long time ago. But I did want to put that plug in. But I do have my master's from UMO, only not in structures. Anyway, I'll get on to it now. Today I'm gonna talk about the GBeam. Everybody's familiar. They've heard enough of it. It's been mentioned quite a few times, especially the Gristmill Bridge. So the presentation, I'm just gonna line up here, the beginning and take us to where we are today. So beginning 2015 was when we started the research and development for GBeam. And what we recognized was the fact that, we had the arch system as a company. And that really, it obviously it's used, it's a good product. We use it. We get projects all the time on that. But the primary thing is it's only really addressing about 10% of the bridge projects that are in the country. That's where the arch system fits the topography in the site. So we needed something for the company in terms of, traditional beam, concrete deck type of bridge. So we went to the University of Maine and we set up some groups and some committees and we met, and that started in 2015. Research and development is ongoing, but primary part of it was done between 2015 and 2018. And then in 2018, based on the research and the developments at the University of Maine, we licensed the technology from the University of Maine. And then 2020 is the first bridge. First manufacturing process. Well, when you're talking about structures that are large, we went to where they do large structures, which is the boat industry. And we started looking at the boat industry and how they did vacuum infusion, how they use that process. And we pretty much modeled it after that. So as you can see there in the picture on the left-hand side, we have a wood form, which is where we started. And that created the girders that are in Gristmill Bridge. It was challenging. I won't try to sugarcoat it. A lot of people that are in this room came to the plant and saw it. A lot of work went into it, and now it's a plaque on the wall. Each layer, you had to lay it up layer by layer, and I'll talk about that in a minute. So this is the installation, the first project, and the site is about 1.5 miles from my house. So I don't know how it got picked for a pilot, but that's where it ended up. I think it was a conversation with Wayne, and I happened to see a soil boring crew so it's all the geotech's fault. As you know, geotechs are always to blame for everything. So I went by and I saw the drill crew out there and they were taking borings at this bridge location, which was on my way to Dunkin' Donuts. And I said, they're going to replace this bridge. Wouldn't this be a great place to pilot this new technology? And the rest is history. So Gristmill project itself, 75-foot span, five girders, carbon and glass fibers, carbon used in the bottom flange, and then glass in the top flange. And contractor first time, one of the comments they made that was really good was that he said, he says, we can put the utilities on the bridge and then put the bridge into place because of the weight. And on a traditional bridge, we would have a lot bigger crane to do that. And it was a safer job by there's a lot of utilities under that bridge. So DOT got a big award. And it's the Transportation Awards, AASHTO Transportation Awards in NASTO. And you can see the commissioner, and I don't know where Greg went, but he's in the picture, and Chief Engineer Joyce Taylor. So changes over the course of from like where we were then, and gaining efficiencies and doing things differently, lessons learned, and where we're heading now. So wooden mold is out. It's just too much. Doing one of those for every project, it would be not cost effective. So we went to a steel mold that is adjustable for camber and will fit projects anywhere from 40, 50, 55 feet. And the other things we did is we worked with a firm also in Maine that works with composite textiles. They do carbon glass, and we started to develop what we call a 3D. You've heard that before, 3D fabric. It's very thick and it's stitched together. And we did a lot of studying on flow rates of the resin, so that we could make sure that on some of these longer span bridges, you've got very, very thick composites. And you want to make sure that the resin is evenly distributed, but you're also up against time, because once you dose with the accelerator into the resin, you've got a certain amount of time before it is gelled and you can't do any more with it. So we did a lot of time studies and a lot of research to get there. The other thing that was mentioned down there, we did learn that you can use, we got FRP staples to hold layers together, as opposed to, we use very little glue now. So changes, fabrication layout. One of the big things that we did, Gristmill Bridge, you saw a lot of steel bolts that were shear connectors to get your composite action between the concrete deck and the girder. Well, working with the university, we developed a new system. When you can see it there, we've infused bridges into the top flange, and that provides a significant amount of composite action. We still, as you know, for redundancy, we still have bolts. I think the Route 69 bridge in Hamden, they use stainless steel bolts. You can use galvanized as well as regular steel. The future, we'll be seeing composite bolts. We're not there yet, but we will be. Second up is, you can see the typical things we were doing with putting all one bridge on a truck, and the easy, we move it around. We move these girders around in the shop on wheel trolleys. So very lightweight. If you've ever been to a steel fabricating plant or a precast plant, they have to have huge overhead cranes and everything else in order to move these things around. We'd like to have a plant with huge overhead cranes, but we don't yet. Twin Bridge, that's the second. It's not actually the second bridge that we did. We did the bridge in Sun Island, which came before Twin Bridge, and we've got other bridges lined up as well into the future, and I'll get to that in a minute. But this is also in Hamden, Maine. The units were built last year, but they were installed this year, and they were installed just a couple days ago. And you can see, it's 3 precast modules, and there were other presentations that talked about the lightweight and ease of installation and all that. This is Rhode Island. This is Cottrell Bridge. This is 38-foot span. This one is being installed end of the month. And it's presently all precast, and it's all ready to go. and will be installed in Rhode Island. Sun Island, that was the one I talked about, the truck that took the girders down. It was precast by one of our friendly contractors in Florida, and then trucked to the site and installed. We did 2 spans of a multi-span bridge, and basically modeled what they had there before as far as dimensions. And that's the advantage of using composites, is we could do a couple things that's unique in the industry. Is we can customize the depth, either by adding more carbon fiber. We can give which obviously in Florida, they're very interested in sea level rise, and being able to give them at least or better clearance on their bridges. Upcoming projects. Close your eyes, Wayne. Upcoming projects that we hope. So anyway, there's California Wildlife Crossing, Northern California. That's a big project for us. It's quite wide. It's 116 feet, 116-foot span. There's a little bit of a controversy on the team. And by the way, that's the whole team over there, AIT team. And so there's a little bit of controversy there, is when we start to set what's the maximum span that a GBeam can do. And we keep pushing the envelope, and that's what we do. And we use, University of Maine is very helpful there. And I've never really given an answer, but I've got 2 engineers over there, and one says 115 and the other one says 120. So I'll go with the 120 for now. I also have the argument about there's some people in my organization that practice engineering without a license. So anyway, the other bridges we've got in the pipeline is Winterberry Bridge in Marco Island. It's going to be advertised for construction in December. The design's all done. And obviously that one is unique because it was a community that they had a girder bridge, and they want to somehow make it into an arch bridge without using arches. They'd rather use G-beams to do, and it's got quite a camber built in. I think it's 17 inches, something like that. So that'll be definitely an interesting project. Rhines Hill Bridge, Wayne touched on that. Solon, he touched on that. Stillwater Bridge replacement in Old Town, Maine. That's right out here. It's posted. It's posted for 60,000 pounds. They need a bridge real bad. University is right here. We think we may be able to provide a solution. And the future of GBeam. This is where I asked my team to close their eyes for a minute. So we really think that that G-beams can be pultruded, which they're big and they require a certain type of machine. And I got a call last night from one of my mechanical engineers that works with us, who works particularly in the machine type design and operation. And he says, Ken, he says, you're going to need a line that's probably close to 250, 300 feet long, right? And I says, really? Well, can we go higher? Can we do like a mezzanine? And he says, yeah, I suppose we could do that. So these machines the machine will have to be big that pultrudes girders of the size that we're talking about. But we're in a process. We're working with the university. We've got a committee, and hopefully within the next, certainly a few months, we will have a concept on paper, and look forward to pultruding our first girder. So GBeam is leading the way in how we think about design in small and medium-sized bridges. And I think that there's a big future for GBeam as well as composites in general. There's one other slide I wanted to point out, is the one up there with, that actual picture is hung in my office. And I came across that quite a while ago, especially the quote. It didn't have the picture of the Grist Mill Bridge on it, but it had the picture of the Brooklyn Bridge on it. And when you think back to when the Brooklyn Bridge was extremely innovative for the time. And they did all kinds of construction techniques, and they used all kinds of materials that had never been used before. They were manufactured specifically for that bridge. And guess what? It's still there today. So with that, I'll close. Thank you.